Continuation of the previous video. Today we're going to learn about radioisotopes and some other aspects. Radioisotopes, also known as radioactive isotopes or radionuclides, are isotopes of chemical elements that exhibit radioactivity. They have unstable atomic nuclei and undergo radioactive decay, emitting radiation in the form of alpha particle, beta particle, or gamma rays. Radioisotopes have diverse applications in science, medicine, industry, and environmental studies. Key concepts in radioisotopes. Radioactive decay. Radioisotopes decay over time at a constant rate following specific decay pathways. Common types of decay include alpha decay, beta decay, and gamma decay. Half-life. The half-life of a radioisotope is the time it takes for half of a sample of the isotope to decay. So different radioisotopes have varying half-lives ranging from milliseconds to millions of years. Then radiation types. Radioactive decay can result in the emission of alpha particles, beta particles, and gamma rays, each with different properties and applications. Then applications. Radioisotopes are used in various fields including medicine, diagnostic, and cancer treatment. Then industry, radiography and sterilization, environmental studies, dating and tracing, and nuclear energy, power generation. Significance and application of radioisotopes. Medical imaging. Radioisotopes are used in medical imaging techniques like positron emission tomography and single photon emission computed tomography SPECT to diagnose disease and assess organ function. And cancer treatment. Radioactive isotopes are employed in radiation therapy to target and destroy cancer cells while minimizing damage to healthy tissues. Then industrial applications are also there. Radioisotopes are used for radiography to inspect wells, detect flaws in materials, and sterilize medical equipment and food products. Then environmental tracers. Radioisotopes such as carbon-40 and tritium are used to trace the movement of substances in the environment, study groundwater flow, and date archaeological and geological samples. So in conclusion, the carbonate system, saturated and unsaturated hydrocarbons, and radioisotopes are important concepts in chemistry and related fields. Next, composition of air. Particles, ions, and radicals in the atmosphere. Composition of air. Air is a mixture of gases that makes up Earth's atmosphere. It is a complex mixture composed primarily of nitrogen, oxygen, argon, and carbon dioxide, and trace amounts of these other gases. Understanding the composition of air is essential in various scientific disciplines, including atmospheric science and environmental science. Key components of air. Nitrogen. Nitrogen is the most abundant component of air, making up approximately 78% of the atmosphere. It is a diatomic molecule N2 and is chemically inert under most conditions. Then oxygen. Oxygen is the second most abundant component, constituting about 21% of the atmosphere. It is essential for respiration and combustion. And argon. Argon makes up approximately 0.93% of the atmosphere. It is an inert gas and is often used in various industrial applications. Carbon dioxide. Carbon dioxide is a greenhouse gas making up about 0.04% of the atmosphere. It plays a crucial role in Earth's climate and photosynthesis. Then trace gases. The atmosphere also contains trace amounts less than 1% of other gases, including neon, helium, methane, krypton, xenon, and among others. Water vapor. Water vapor is a variable component of the atmosphere, typically ranging from 0 to 4% by volume. Its concentration varies with location and altitude and plays a significant role in weather and climate. Particles, ions, and radicals in the atmosphere. The atmosphere contains not only gases but also various particles, ions, and radicals that contribute to its chemistry and physical properties. These components have important implications for atmospheric process, air quality, and environmental studies. Then key components in atmosphere. Aerosols. Aerosols are tiny solid or liquid particles suspended in the atmosphere. They include dust, smoke, pollen, and pollutants. Aerosols can affect climate by scattering or absorbing sunlight and by serving as cloud condensation nuclei. And ions are charged particles in the atmosphere. They are often formed by the ionization of gases due to cosmic rays or solar radiation. So common ions include positively charged ions, cations like H plus and NO2 plus, and negatively charged ions, anions like SO2 minus and Cl minus. Radicals are highly reactive molecules or atoms with unpaired electrons. They play a critical role in atmospheric chemistry, participating in various reactions. Examples include hydroxyl radicals, OH, nitrogen oxides, NOH, and ozone, O3. Particulate matter. Particulate matter consists of tiny solid or liquid particles, including dust, soot, organic aerosols. PM can have adverse health effects when inhaled and can also impact visibility and air quality. Particulate matter. Okay, significance. Air quality. The presence of particles, ions, and radicals in the atmosphere can influence air quality, affecting human health and ecosystems. High levels of pollutants and particulate matter can lead to smoke and respiratory problems. Then chemical reactions. Radicals play a crucial role in atmospheric chemical reactions, including the breakdown of pollutants and the formation of ozone, which has implications for air quality and climate. Then cloud formation. Aerosols and ions serve as cloud condensation nuclei, influencing cloud formation and properties, which in turn affect precipitation patterns and climate. Then climate change. Aerosols can have both warming and cooling effects on climate, depending on their composition and interaction with solar radiation and clouds. And atmospheric processes. Understanding the behavior and interaction of particles, ions, and radicals is essential for studying various atmospheric processes, including photochemical smog formation, acid rain, and stratospheric ozone depletion. So, in conclusion, the composition of air encompasses not only the major gases but also various particles, ions, and radicals that play a significant role in atmospheric chemistry, air quality, and environmental process. In chemical speciation and chemical processes in the formation of inorganic and organic particulate matter. Chemical speciation refers to the distribution of chemical species, atoms, ions, molecules of a particular element or compound in various forms or states in a given environment or ecosystem. So, it is a fundamental concept in environmental chemistry and plays a crucial role in understanding the behavior, toxicity, and fate of chemicals in natural and anthropogenic systems. Key concepts in chemical speciation. Chemical species. Chemical species can exist in various different forms such as elemental, ionic, molecular, or complex species. For example, the element mercury can exist as elemental mercury. Chemical species can exist in different forms such as elemental, ionic, molecular, or complex species. For example, the element mercury can exist as elemental mercury, inorganic mercury ions, or organic mercury compounds. And partitioning. Chemical species can partition or distribute among different phases in a system, including air, water, soil, sediments, and living organisms. So, partitioning depends on factors like temperature, pressure, pH, and chemical properties. And chemical equilibria. Speciation is often governed by chemical equilibria involving reactions, dissolution, precipitation, adsorption, complexation, and redox transformations. These equilibria determine the concentrations of different species. An environmental impact. The speciation of chemicals can greatly impact their environmental behavior, toxicity, mobility, and bioavailability. For example, the toxicity of heavy metals can vary depending on their chemical form. Then, applications of chemical speciation. Environmental risk assessment. Speciation analysis helps assess the risk of pollutants by considering their various forms, which may differ in toxicity and mobility. And water quality. Speciation of ions like arsenic, chromium, and mercury is crucial in evaluating water quality and ensuring compliance with the regulatory limits. Biogeochemical cycles. Understanding the speciation of elements like carbon, nitrogen, sulfur, and metals is essential for studying biochemical cycles in ecosystems. Then chemical processes in the formation of inorganic and organic particulate matters. Particulate matter (PM) refers to tiny solid or liquid particles suspended in the air. These particles can be either inorganic or organic in nature and are a significant component of air pollution. Understanding the chemical processes involved in the formation of PM is crucial for addressing air quality and environmental concerns. Then, formation of inorganic particulate matter. Primary particles in organic PM can originate directly from natural and anthropogenic sources. Examples include dust, soot, and metal particles emitted from industrial processes and combustion. Secondary particles. Primary particles are nothing else but particulate matter created directly from natural and anthropogenic sources. For example, dust, soot, and metal particles emitted from industrial processes and combustion. And secondary particles, inorganic particulate matter can also form in the atmosphere through secondary process. Key mechanisms include nucleation, formation of new particles from gas phase precursors often involving sulfuric acid and ammonia. Coagulation, collision and aggregation of smaller particles to form larger particles. Condensation, gaseous species condense into existing particles, increasing their size. Then chemical reactions. Chemical reactions involve gases like sulfur dioxide, SO2, nitrogen oxide, NOx, ammonia, and volatile organic compounds. Can lead to the formation of inorganic PMs such as sulfates, nitrates, and ammonia salts. Then formation of organic particulate matter. Primary organic aerosols. These are directly emitted solid or liquid particles of organic origin such as soot from combustion engines or pollen from plants. Then secondary organic aerosols from the atmosphere from the oxidation of volatile organic compounds. Key processes include photodissociation. Volatile organic compounds break down into radicals under sunlight. Then oxidation. Radicals react with oxygen and other atmospheric constituents, forming oxidized organic compounds. Then condensation. Oxidized organics can condense and form SOA particles. Then biogenic sources. Some organic PM such as terpenes from trees is biogenically derived and contributes to organic aerosols in the atmosphere. Then significance and implications. Air quality. Understanding the formation of inorganic and organic PM is crucial for managing air quality as PM is a major contributor to respiratory and cardiovascular diseases. Then climate effects. Both inorganic and organic PM have direct and indirect effects on climate as they can scatter or absorb sunlight, influence cloud formation, and impact radiative forcing. Then health impact. Different PM types can have varying health effects, with fine particles often being more harmful due to their ability to penetrate deep into the respiratory system, and that can be very dangerous. Then environmental fate. The composition and sources of particulate matter affect its environmental fate, transport, and deposition in ecosystems with potential consequences for soil and water quality. So in conclusion, chemical speciation and the processes involved in the formation of organic and inorganic particulate matters are essential topics. Then thermochemical and photochemical reactions in the atmosphere. Thermochemical reactions in the atmosphere. Thermochemical reactions in the atmosphere involve the release or absorption of heat energy during chemical processes. These reactions are vital in understanding the energy balance of the Earth's atmosphere. So thermochemical reactions in atmosphere. Thermochemical reactions in atmosphere involve the release or absorption of heat energy during chemical processes. These reactions are vital in understanding the energy balance of the Earth's atmosphere as well as the formation and transformation of various atmospheric constituents. Key concepts in thermochemical reactions. Exothermic reactions. Exothermic reactions release heat energy into the surroundings. In the atmosphere, common exothermic reactions include combustion processes such as the burning of fossil fuels, which release heat and produce greenhouse gases like carbon dioxide. Then endothermic reactions. Endothermic reactions absorb heat energy from the surroundings. These reactions play a crucial role in cooling the atmosphere and include processes such as the evaporation of water, latent heat absorption, and ozone formation in the stratosphere. Once again, I'm going to read this. Exothermic reactions. Exothermic reactions release heat energy into the surroundings. In the atmosphere, common exothermic reactions include combustion processes such as the burning of fossil fuels, which release heat and produce greenhouse gases like carbon dioxide. Then endothermic reactions. Endothermic reactions absorb heat energy from the surroundings. These reactions play a crucial role in cooling the atmosphere and include processes like the evaporation of water, latent heat absorption, and ozone formation in the stratosphere. Heat of formation. The heat of formation represents the enthalpy change when one mole of compound is formed from its constituent elements in their standard states. It is a fundamental parameter in thermochemical calculations. Then examples of thermochemical reactions in the atmosphere. Combustion of fossil fuels. The combustion of hydrocarbons, methane, ethane in the atmosphere releases heat energy and form carbon dioxide and water vapor. So ozone formation in the stratosphere, ozone is formed through endothermic reactions involving oxygen molecules and ultraviolet radiation in the stratosphere. These reactions absorb UV energy, providing a protective ozone layer. So, next process, latent heat of evaporation. When water evaporates from the Earth's surface into the atmosphere, it absorbs heat energy, cooling the surrounding environment. This latent heat releases influences weather and climate. Significance and implications of thermochemical reactions. Energy balance. Thermochemical reactions are essential for maintaining the Earth's energy balance. The absorption and release of heat energy influence temperature profiles in the atmosphere. Then climate change. Thermochemical reactions, especially those involving greenhouse gases like CO2 and water vapor, play a significant role in Earth's radioactive forcing and climate change. Atmospheric stability. Understanding exothermic and endothermic process helps explain atmospheric stability, temperature inversions, and vertical distribution of temperature in the atmosphere. Then photochemical reactions in atmosphere. Photochemical reactions in atmosphere are driven by solar radiation, primarily in the ultraviolet and visible regions. These reactions are responsible for the formation and destruction of various atmospheric constituents, including ozone, radicals, and pollutants. Key concepts in photochemical reactions. Photodissociation. Photodissociation is the breaking of chemical bonds within molecules or atoms due to the absorption of photons, light particles. It's a common process in photochemical reactions. And absorption spectra. Different molecules and compounds have specific absorption spectra indicating the wavelengths of light they can absorb. So, photodissociation often occurs when molecules absorb UV radiation. Then, ozone layer. Photochemical reaction in the atmosphere in the sun, stratosphere, are crucial for the formation and maintenance of ozone layer. Ozone is formed by photodissociation of oxygen molecules and is destroyed by reactions involving radicals like chlorine and bromine. Then examples of photochemical reactions in the atmosphere. Ozone formation. Ozone formation is that stratosphere involves the photodissociation of oxygen molecules by solar radiation, leading to the formation of ozone. O2 plus UV, 2O. O plus O2, M is equal to O3 plus M. M in the sense third body collision. Smog formation. Photochemical smog, often found in urban areas, results from the photochemical reaction of nitrogen oxides and volatile organic compounds in the presence of sunlight, leading to the production of ground level ozone and other pollutants. Photolysis of pollutants. Pollutants like nitrogen oxide and sulfur dioxide undergo photolysis, where UV radiation breaks them down into radicals and other reactive species. Significance and implications of photochemical reactions. Ozone layer protection. Photochemical reactions play a vital role in protecting the ozone layer in stratosphere by continuously forming and depleting ozone. So, understanding these reactants is essential for ozone layer monitoring and policy measures. Then, air quality. Photochemical reactions are involved in the formation of ground level ozone and smog, which can have adverse effects on human health and air quality. Then, radiative forcing. Ozone and other photochemically produced species can influence radioactive forcing and climate by absorbing and scattering sunlight in the atmosphere. Then, pollution control. Understanding the role of photochemical reactions in the formation of pollutants informs strategies. Oxygen chemistry. Oxygen is a diatomic molecule composed of two oxygen atoms bound together by a double covalent bond. It is one of the most abundant elements on Earth and plays a central role in various chemical and biological processes. So, understanding oxygen chemistry is crucial in atmospheric science, environmental chemistry, and biochemistry. Key concepts in oxygen chemistry. Oxygen's role in respiration. Oxygen is essential for the respiration of living organisms. In cellular respiration, cells use oxygen to extract energy from glucose through a series of chemical reactions, producing carbon dioxide and water as byproducts. Then, reactivity. Oxygen is a highly reactive element. It readily participates in combustion reactions where it combines with other substances, releasing heat and energy. For example, the combustion of hydrocarbons and fossil fuels involved the reaction of oxygen with carbon and hydrogen. Oxygen in Earth's atmosphere. Molecular oxygen makes up approximately 21% of Earth's atmosphere by volume. It is essential for the survival of aerobic organisms. Then oxygen cycle. The oxygen cycle involves the continuous exchange of oxygen between the atmosphere, biosphere, hydrosphere, and lithosphere. It includes processes like photosynthesis, respiration, and chemical reactions in the Earth's crust. Then ozone chemistry. Ozone is a triatomic molecule composed of 3 oxygen atoms. It is a vital component of Earth's atmosphere, found primarily in the stratosphere, where it forms the ozone layer. Ozone chemistry is significant in atmospheric science, climate studies, and environmental protection. Then key concepts in ozone chemistry. Ozone layer. The ozone layer is a region of the stratosphere containing a higher concentration of ozone molecule. It plays a critical role in protecting life on Earth by absorbing and blocking a significant portion of harmful ultraviolet radiation from the sun. Then ozone formation. Ozone is formed in the stratosphere through a photochemical reaction involving oxygen molecules and solar UV radiation. Ozone depletion. Ozone molecule in the stratosphere can be destroyed by various chemical reactions, including those involving chlorine and bromine compounds. Human-made substances like chlorofluorocarbons have been responsible for ozone depletion, leading to the ozone hole. Then photochemical smog. Photochemical smog is a type of air pollution that results from complex photochemical reactions involving sunlight, nitrogen oxide, volatile organic compounds, and other pollutants. It is often associated with urban areas and can have detrimental effects on human health and its environment. Then, key components in concepts in photochemical smog. Formation. Photochemical smog forms when primary pollutants such as NOx and volatile organic compounds are released into the atmosphere from sources like vehicles, industrial processes, and natural emissions. Then, reaction in sunlight. In the presence of sunlight, NOx and VOCs undergo a series of chemical reactions that lead to the formation of secondary pollutants, including ground level ozone and other harmful compounds. Components. The major components of photochemical smoke include ground level ozone, nitrogen dioxide, and peroxyacetyl nitrate, and other oxidants and particulate matter. Then, health effects. Photochemical smoke is associated with respiratory problems, eye irritation, and other health issues. It can worsen conditions like asthma and bronchitis. Significance and implications. Primary significance is health impacts. Photochemical smoke poses significant health risks to urban populations. It can aggravate respiratory diseases and lead to cardiovascular problems. Then air quality. Monitoring and controlling photochemical smoke are essential for maintaining good air quality in urban areas. Regulations and measures to reduce emissions of NOx and VOC are common strategies. Then environmental effects. Photochemical smoke can harm vegetation, including crop damage and forest decline. It also contributes to the formation of acid rain. Then stratospheric ozone. The study of ozone chemistry in the stratosphere, particularly the ozone layer, is essential for understanding its depletion and the implication for increased UV radiation reaching the Earth's surface. In conclusion, oxygen and ozone chemistry, along with formation and effects of photochemical smoke, are important topics in atmospheric science and environmental chemistry. Next important topic, hydrological cycle. Water as a universal solvent. Hydrological cycle, also known as the water cycle, is a continuous natural process that describes the movement, distribution, and transformation of water on Earth. It involves the exchange of water between the Earth's surface, the atmosphere, and underground reservoirs. The hydrological cycle plays a fundamental role in regulating Earth's climate and supporting life on our planet. Then, key processes in the hydrological cycle. Evaporation. The cycle begins with the heating of Earth's surface by solar energy. This heat causes water from oceans, lakes, rivers, and land surfaces to evaporate and transform into water vapor. Then, condensation. As moist air rises into the atmosphere, it cools and water vapor condenses into tiny water droplets or ice crystals, forming clouds. Then, precipitation. When these cold cloud droplets combine and grow in size, they eventually become heavy enough to fall back to the Earth's surface as precipitation, which can take in the form of rain, snow, sleet, or hail. And infiltration. Precipitation that falls on land can infiltrate into the ground, replenishing groundwater aquifers. Some of this water may be taken up by plant roots and transferred back into the atmosphere, a process known as transpiration. Then surface runoff. Excess precipitation that does not infiltrate into the ground becomes surface runoff, flowing into rivers, streams, and eventually back into the oceans. Then subsurface flow. Some water may move through underground pathways, eventually reaching rivers or contributing to groundwater recharge. Significance and implications of the hydrological cycle. Water supply. The hydrological cycle is responsible for replenishing freshwater sources, including surface water bodies and groundwater aquifers, which are essential for drinking water, agriculture, and industry. Then, climate regulation. The movement of water vapor in the atmosphere plays a critical role in regulating its temperature and climate. Water vapor acts as a greenhouse gas, trapping heat and moderating temperature extremes. And erosion and sediment transport. The flow of water in rivers and streams erodes landscapes and transports sediments. This has geological and ecological implications, including the formation of river valleys and deltas. Then, ecosystem support. Water availability is crucial for maintaining terrestrial and aquatic ecosystems. Wetlands, lakes, and rivers provide habitats for numerous species and support biodiversity. Weather patterns. The hydrological cycle is closely linked to weather patterns and atmospheric circulation. Changes in cycle can lead to variations in precipitation patterns and weather events. Then, water as a universal solvent. Water is often referred to as the universal solvent because of its unique ability to dissolve a wide range of substances. This property is essential for life on Earth and has profound implications for chemistry, biology, and environmental science. Concepts in water as a universal solvent. Polarity. Water is a polar molecule, meaning it has positive and negative end due to an uneven distribution of electrons. This polarity allows water molecules to attract and surround charged or polar molecules, facilitating their dissolution. Then, hydrogen bonding. Water molecules are held together by hydrogen bonds, which are weak electrostatic attractions between the positively charged hydrogen atom of one water molecule and negatively charged oxygen atom of other. These hydrogen bonds make water an excellent solvent. Then, dissolving solutes. Water can dissolve a wide range of solutes, including salts, ionic compounds, acids, bases, and polar molecules. It can break down these substances into ions or molecules, forming aqueous solutions. Then, hydration. When a solute dissolves in water, water molecules surround and solvate the solute particles, allowing them to disperse evenly throughout the solution. Then, significance and implications of water as universal solvent. Biological processes. Water's ability to dissolve and transport nutrients, ions, and gases is fundamental for biological process. It facilitates the transport of nutrients within cells and the circulation of blood in organisms. Then, chemical reactions. Water is the medium for many chemical reactions, both in living organisms and in industrial process. It acts as a solvent for reactants and helps facilitate chemical transformations. Environmental chemistry. Water solvent properties play a crucial role in the transport and transformation of pollutants in natural systems. It influences the fate and transport of contaminants in soil, groundwater, and surface water. Then, weathering and erosion. Water capacity to dissolve minerals and rocks contributes to weathering and erosion processes, shaping landscapes over geological time scales. Then, food and beverage industry. Water roles as a universal solvent is essential in food preparation, flavor extraction, and the creation of beverages, making it a key ingredient in the food industry. So, in conclusion, the hydrological cycle is a fundamental earth process that governs all this. Next, concept of DO, BOD, and COD. Dissolved oxygen. Dissolved oxygen refers to the amount of oxygen that is present in water and available for aquatic organisms to spare. It is a critical parameter in water quality assessment and is essential for the survival and growth of aquatic life. DO levels are influenced by various factors, including temperature, pressure, and the presence of oxygen-consuming substances. Key concepts in dissolved oxygen. Sources of DO. DO in natural water bodies primarily comes from two sources, which are the Atmospheric dissolution, oxygen from the atmosphere can dissolve into water at the water air interface. And photosynthesis, aquatic plants and algae produce oxygen through photosynthesis, contributing to DO levels during daylight hours. Tomorrow we are gonna learn this once again, this dissolved oxygen portion. Thank you for listening.